and I have graded, and then I haven't got the time to upload your grade yet. I will do it on probably Sunday night. Okay, so hopefully give you a good weekend, and then until Sunday. So I will do it on Sunday, and then I will go over it on Monday. The homework 3 questions, homework question has been uploaded. So from today, I will go over a few examples, and then we will get into the another type of the indeterminate problems for chapter 3. So probably after today, you can begin to work on a few homework questions, and gradually, that is the goal. And we don't have a lectures on Wednesday, and we have a test on Monday. So basically, right now we only have one lecture get into the chapter 3. And that is about here. I'm going to give you a review of what we have done last Friday. So last Friday we have the model. So this is the shaft, and with the solid shaft with the radius, let me use C. And the C is the notation from our textbook. And for this, it is under torsion. So the torsion, here let me use a double arrow. So that indicate is this, use our right hand rule and use our thumb to align the double arrow. So the four fingers give us the circulation of the torsion, which is T. And the same thing for here, that circulation is here. So that will guarantee this is under static equilibrium. So under these situations, say if we take a cross section, and let me draw the cross section here. On these cross sections, and if let's take a look at from this viewpoint, so the torsion will be applied in these orientations. And on this cross section, we can display the distribution of the stress. For example, let me take this radial. The length, the segment, then the distribution of the stress is this. And the surface, that should be tangent to the point, and in the tendency of the same circulation in the as T. And then the profile, the magnitude of this magnitude is tau equal to Tc over J. Okay, and for any other point inside these cross sections, the distribution of the magnitude of the shear stress actually is form of linear distributions. So that means we can identify any radial distance, for example, rho. So at this distance, the magnitude of the shear stress equal to tau equal to T rho over J. So that means here the only parameter to govern the magnitude is the distance, the radial distance from the center here. And in the shaft, the maximum stress is always on the outside here. So the maximum stress is always taking the maximum value of the rho, which is the radius C. And also, let me call this is end A. This is the end B. We also talk about the angle of the twist. So that means B relative to A, and that is Tc TL over Gj. G is the rigidity modulus of the shaft. J, we call the polar moment of inertia, and by this formula. And L is the length. L is the length of the shaft, and P is the given torque. So that is the only two equations here we're going to deal with in these chapters. And then we can try to see the example to practice the two questions. The first one, I uploaded a revised chapter 3 slides. And if you wish, I only add one more slide. That's one example on page 27. So that means I just sent an email before I came here. So you can download that email and just only print out the page 27 for that new example if you already have the old one. Okay, we keep the things and then we can work on, let me work on these examples here. Basically, let me redraw these patterns, and that is not so clear. So, if we have a shaft, and here we apply basically the shaft is supported by certain mechanism we call bearing. Okay, the shaft is basically snagging to the bearing and then to sustain the free rotation of the shaft, but not to move. Okay, so here this on the two ends, and we have two bearings. So basically to fix, and here we have A, B, C, D, E, F, and in this drawing here you can see the kind of the pulley. The pulley here is work as the rigid body. And then to transmit the torque to the shaft. Okay, so that's the meaning of the pulley. So here, let me follow up these notations. So for example, here, let me translate it. So for this torque, is rotating in this way. So you, with my forefinger, to follow up. So that torque at B is working in this way. So let me use this one. So that's the torque at B, and that is 35. And the unit is the pound per inch. And at C, use my forefinger to follow the circulation, so the direction is 20. And at D, that is in that way, so pointing to that way is 40. And at E, that is, you pretty much, it's not so clear, but that is in this way. Okay, so that is 25. Okay, so basically through the full pulleys here, we apply the torques to twist the shaft. You can see this one here has 35 and 25, in total 50, 60 go that way. 20, 40, in total 60 go that way. So basically in this shaft, everything is in static equilibrium. Okay, and now for this case, this is our generic model. So that means, again, for example, if I would take a cross section here, then we can analyze the reaction torque in that cross section. Then we'll be able to plug in our generic model. Yes?
Just to confirm units. Are we using 25 pounds, or the 25 pounds per foot or inch, because we're switching between them?
Oh, foot. Sorry.
Yeah.
Let me switch to foot. Yeah. Thank you. Thanks. So again, the first step is to analyze the reaction torque in each segment. The same technique we have done in chapter, like in chapter 2. So. Through each, here we divide into 1, 2, 3, 4, 5 segments. And then this direction, this is 0. And for the sign convention is this. For any segment, let me say if the torque is applied like this, let me say that is positive. And say put downward here, the torque applied to that free body diagram would be like this. So with this sign convention is arbitrary. Okay, basically depends on your preference, and then we can begin. So now again we begin to take the free body section, and for example in this section I pick out anywhere. So that is the free body diagram. Let me draw that here. So here you can see in this free body diagram of this portion, actually there's no torque there. So that should be 0, right? Everywhere, as long as this section I chose is not to exceed point B, then doesn't matter where inside there, that should be 0. So the torque should be 0 everywhere in that segment. And now we move, and so pick the section in the second segment. So in this free body diagram, we have to include the torque applied at B. Here is 35. Okay, so that is our reaction here. So here the reaction torque must be 35 to be balanced with this one. So from here you can see in this segment that really doesn't matter. In this segment doesn't matter where we pick the cross section. Result will be always 35 like that. Okay, so according to the sign convention here, 35 should be going up the downward here. The magnitude is 35. Okay. Let me turn on. And then we move our selections to here, to the third one. And to the third one, let me draw the bottom here. So here is the 35 applied at B, and here is 20 applied at C. So now 35 go that direction, 20 go this direction. So here we must be balanced by how much? By 10. 15, yes. So that should be here. The magnitude is 15. Okay, now we move on to the next segment. So that would be like this, and 35, 20, and here is 40. So here 60 go leftward, 25 go that way. So here on here we have to balance by 25. Okay, so that on this cross section, that is 25 going outside here, so that should be 25 here. And now we move to the final segment here. To the final segment, either way, I don't want to take the long, you can either take the long way from the left to here, or either we can pick this cross section, this free body diagram. So here, let me pick up the right part of the free body diagram. Okay, this portion here. So here, you can see that is 0 everywhere. So the final portion is 0. Okay. So once we have everything, then we can begin to calculate. For example, let me call this segment 1, 2, 3, 4, 5. And with appropriate geometry and dimensions, we will be able to do some calculations. And so, for example, here for D is, for example, the shaft 0.75 inches. So in this one, we can calculate tau. In portion 1 will be TC, the maximum tau in each portion. TC over J, that will be 0. Then in second segment, equal to TC over J, and C equal to, okay, let me write it up, and J equal to pi over C to the 4th power. So before we do the calculation, we can simplify this a little bit. So that is 2T divided by pi C to the cube. So we plug in the numbers here. The torque In the second segment is 15. 2 times 15, and 15 pounds per foot.
2 times 35.
Oh, yes, thank you. That is 35. And this is 35 is pound per foot. And here we try to convert into the inches. So that is the 12. 1 foot is 12 inch. Okay, so and then pi times c. C is 0.075 inch divided by 2 cube.
Um,
0.75.
Quick question about your units there for your conversion. You're saying, is that pound per foot or pound times foot?
Oh,
Because
pound
it's-
times foot. Yes.
Okay, so we would
Yes.
swap our conversion.
Yes. Yes. Okay, that yes. And then 1 foot, 12 inch. Okay. So in this way, we can cancel the foot away. So that means here this result will be 5.07, 5070 psi, and or 5.07 ksi. Okay, and then for this third 3, 4, 5 segments, basically repeat the same process. For these demonstrations, the focus is to show you how to make this graph. And the polar moment inertia, as long as we know the radius, you should be able to calculate using this equation. Yeah, just here. And this is for solid. For solid shaft of radius c, and that is this. And for hollow shaft, and for example, we have the inner radius is ci, and we have the outer radius co. So the j will be equal to pi over 2 co to the fourth minus ci to the fourth, and that is for the hollow shaft.